Okay, so we are now going to put together some of the relationships between centripetal force and gravity. So, as we've talked about previously, centripetal force must always be caused by some external force. And as I mentioned in my last video, as the Earth is traveling around the sun, it is gravity that is causing it to change directions. So, what that means to us is that centripetal force is going to equal the force of gravity. That is, that mass of the um, the mass of the planet times velocity squared over r has to equal big G, the mass of the planet, times the mass of the star divided by the radius squared, where the radius is the distance between the two objects, the distance between the planet and the distance between the star. And so looking at this, you can see the mass of the planets cancel out, and you should see that r and r squared are also going to have a cancellation. So we would get something like v squared is equal to big G, the mass of the star, divided by the radius, which works out very nicely to give us a very simple way to describe what's happening with the velocity of the Earth, for example, as it's traveling around the sun. As when it's got a smaller radius, a smaller r value, it would have a bigger velocity. The bigger the star, the bigger the velocity. This works out pretty nice. But let's take this to another level, because we know that when an object is traveling in a circular path, that the velocity in a circular path is equal to the circumference divided by the time it takes to go around, the period. Or in other words, 2 pi r divided by the period. Let's work this out a little bit and set this equal to this. And when we do that, I'm trying to get it lined up here, we end up with 2 pi r divided by t squared is equal to G, the mass of the star, divided by the radius. Taking that and squaring it, we get 2 pi 3, 2, 1. Taking that and squaring it, we get 4 pi squared r squared divided by t squared is equal to G times the mass of the star divided by the radius. Now that looks like something that is very basic at this point, but watch what's going to happen next. We are going to get r cubed divided by t squared is equal to G, the mass of the star, divided by 4 pi squared. Or if we flip it, we get t squared over r cubed is equal to 4 pi squared divided by G times the mass of the star. And so now we get Kepler's constant. Right here is the constant for different central bodies to figure out the relationship between t squared and r cubed for any object traveling around it. So if it's a planet and it has a bunch of moons traveling around it, instead of using the mass of the star, you could use the mass of the planet. If it's the sun, like we have here, we plug it in and we get the relationship between t squared and r cubed. Newton's universal gravitation supports 100% the ideas of Kepler and reinforces his ideas of his first, second, and third laws. Newton gave mathematical support to Kepler through this, and we were able to have a deeper understanding of what is happening in our solar system and in the universe as a whole.